So, however, our speaker this evening is not going to be introduced in that way. You're in fact an engineer who's been working for 4 years now in the European Gas Research Group, and you're going to talk about hydrogen as an energy vector. I'm not going to discuss any of the things we talked about, very interesting things we talked about over dinner. I'm just going to ask you to go straight ahead and tell us about the very exciting project you're looking at now, and then we'll take questions from the audience. Over to you, Alexandra, please.
Perfect. Thank you very much for the introduction. So yes, good evening, everyone. Thank you very much to the RSC and to Tim and the colleagues for the invitation. It's a pleasure to be here. So as mentioned, I am not a chemist myself, but I will do my best to make this still interesting for the audience. The European Gas Research Group, so we are an association, we're based in Brussels, mostly with industry and industry gas membership, so research centers and universities as well. And our objective broadly is to have collaborative projects on research topics related to the gas industry and its future. So, of course, that is hydrogen, biomethane, methane emissions. We participate in European funded projects and also in co-funded projects by the industry. And we collaborate with a range of European stakeholders, so the funding programs, Clean Hydrogen Partnership, as well on metrology, SEN for the standardisation link, and a range of associations that you may recognize from the Brussels ecosystem. So and myself, so I'm been working for the association for 4 years, and we have developed sort of a portfolio of projects. Our priorities lie on mostly at the moment these 4 categories. We are developing carbon capture and storage as a new interest point for the association, but we're doing a lot on hydrogen, on biomethane, and on methane emissions. So hydrogen, of course, is a main focus at the moment for the energy sector. Hydrogen is not something new for the chemical industry, of course. It is a majorly present in the industry for chemical purposes. But in the energy sector, it is an up and coming topic. So it is an energy carrier that can solve a range of challenges. Of course, because of the combustion, it's not emitting harmful greenhouse gases. And it depends on the modes of production of hydrogen, which are a big topic that we're not going to tackle today, but that it's important to have clean hydrogen production and ramping it up to increase the savings of emissions from various use cases. So here, this is a diagram for the International Energy Agency, just mentioning that hydrogen is, of course, not a silver bullet, not the only solution, but it is an important part of the range of solutions that have to be implemented in order to reach the scenarios of reduction of emissions. Next to, of course, introduction of renewable energy sources, electrification, carbon capture and storage, and other solutions. And from our side, we have been looking at production, or the whole hydrogen as an energy vector value chain is still being under development. So we have the production of hydrogen, the transport, the storage, and the utilization. The project that I would like to present tonight is one project, was a 3-year project that was funded by the Clean Hydrogen Partnership, in which we were, as an association, a member. And it focused on the end part of the value chain, so the utilization of hydrogen, in particular in its version of blended with the natural gas. So this is a way of getting hydrogen into the existing networks, which is just to introduce a percentage of hydrogen into the existing natural gas network. And the question was, how then do we deal with the endpoints of the utilization of this new mixture, and how do the equipment deal with the change the gas qualities and other elements that can be impacted by switching from natural gas, mostly methane, to a natural gas hydrogen mixture. So this is the project in question. It was called THyGA, as in testing hydrogen admixture for gas applications, received funding from the Clean Hydrogen Partnership and the European Commission. So the objective starts with the idea that introducing hydrogen into the natural gas, the existing energy network, is a way to increase immediately the demand for hydrogen, because of course we have the issue of increasing the demand and increasing the supply of hydrogen, clean hydrogen in particular, to go towards our energy transition goals. And including it into the gas grid provides an already existing way of utilizing this produced hydrogen. However, even though the percentages might not be very high, we will see later, any introduction, even a small percentage or in volume of hydrogen introduced into the gas grid, due to the very high volumes of the gas that is being utilized across the European Union, would already provide a consequent reduction of CO2 footprint from the utilization of this mixture. But it does pose a challenge for the induced equipment, in particular for higher percentages of hydrogen that were not included into the specifications of equipment when it was produced, manufactured, because it was never planned that it would be used for these mixtures. So that was the objective of the project, to research the impacts of this blending and utilization. The focus for this project was on residential and commercial gas applications, which is a consequent market of more than 200 million appliances installed at the moment in Europe. So this is the consortium that did the work. So we have gas companies, consultancy research groups, and the GERG, European Gas Research Group, so as an association, and GasB, a Belgian gas association, which you may be familiar. It ran from 2020 to 2023, and as you can see, with some geographical diversity of the partners. So, to summarize the objectives of the project, we wanted to close the knowledge gaps related to the technical impacts on residential and commercial gas appliances, support the standardization activities to formalize the standardization actions needed to to certify the applications for use with hydrogen blending, which is of course necessary to actually implement in real life this solution of blending hydrogen and natural gas. And study the acceptable hydrogen percentage, so with quite a high variation in terms of the percentage included in the mixtures. So very quickly, this is the structure of the project. So what is interesting for us is that the project did a study of the status of gas utilization technologies. We will see in a couple of slides that it was quite a broad spectrum of various technologies, various applications for cooking, for heating, and all the various types of appliances in those categories. And did some literature research about the existing data for these applications, and then which was supplemented by a very extensive experimental work program. There was a focus on studying the existing standardization rules concerning these applications and how hydrogen would impact them, as well as what needs to be modified for the new standardization to fit our new vision for the system. And recommendations for mitigation measures, so technical as well as standardization recommendations, and standard work package, European work package activities, project management, and communication, dissemination, exploitation. This project was actively supported by an advisory panel group, which is usual. Here it was very useful because in the advisory panel group we had a lot of manufacturers who were very helpful by providing equipment for testing, which allowed the project to have a lot of actual equipment to test the various hydrogen blends on. So this was the starting point of the project. to screen and to segment a very large portfolio of domestic and commercial gas appliances. So we had boilers, water heaters, cookers, catering appliances, space heaters, etc. So more than 50 appliance technology segments, which were, and for all of those there was literature research, particularly on combustion theory for hydrogen mixtures and the impact on the one side and impact on the materials on the other. So some of the topics that were researched were the combustion and gas quality characteristics, the impact of hydrogen on combustion stoichiometry, the laminar combustion velocities, pollutant emissions, CO2 and others, and safety aspects. So the conclusions were that there wasn't consistent data and there wasn't enough data existing about these topics in at least accessible in a published way. So this justified the following slides of the research done in the project. So this is not readable, of course, just to give a view of the impact of the work. So for each of the segments of appliances, we had a classification, and it was developed that was developed for the project and was used later in the testing program. So one topic that I will detail a little bit more is the combustion theory. So this was done through, before the experimental testing was produced, some studies about the impact of hydrogen on basic combustion and gas quality characteristics, in particular combustion stoichiometry, laminar combustion velocities, pollution and safety. So as an example, here we see on the graphic on the left, so you see three lines. The bottom line corresponds to pure methane. The second one, a blend of 30% hydrogen, 70% methane in volume, and the red one on the top to 50% of each gas. So we see that because of the different characteristics of hydrogen and methane, the impact on the combustion.
What are the abscissa and the alternates? Sorry.
Yes.
On the graph that might help us to understand it.
Yes, absolutely. So we have here a graph of the laminar combustion velocity linked to the stoichiometry of on the ordinate of the stoichiometry of the reaction, which is what is illustrated here. That depending on the condition, so we can't just say if we have 30% of hydrogen, we will have this effect, because it is really a range of conditions that are in play. One of them being the stoichiometry operating conditions, because we see here that this is for a premixed heating appliance which is operating in air excess. So if these 2 points that are linked by the arrow, if we go from pure methane to 30% of hydrogen, we increase the air excess ratio, but it does also go towards a higher stoichiometry operating conditions, which means that the increase in the laminar velocity is actually counteracted. So the two effects are counteracting each other, and we don't see a huge increase in the laminar velocity. Whereas here, for a premixed cooking hob, we are operating at sub-stoichiometry conditions, and therefore we have an increase of the laminar velocity that is actually increased. So the two effects are increasing the effect of the introduction of hydrogen into the mix. So this is to say that for this topic, it was really a focus of the project of the dealing with the operating conditions of the equipment. So, for example, we will see later that the adjustment of the equipment by at its installation was identified as a major element of making this switch to blends of hydrogen work, which of course is a challenge because it means that it requires some focus on individual pieces of equipment, so some review by qualified personnel who will be able to make that check or to certify that the appliance will be operating under the right conditions. So the experimental work program of the project was created taking lessons learned from previous projects, European funded in particular, the literature review on combustion science information. It was then created, an experimental protocol was created with the THyGA members and laboratories in the project. And we had a feedback loop with the advisory group with a review after the first test that created a final version of the test protocol used in the project. So 3 types of tests were made during the program. We had short-term tests, small duration, a few minutes to a few hours on different hydrogen and natural gas mixtures. More than 100 appliances were tested, burners in particular, and they covered all the segments identified at the beginning of the project. Long-term tests were done in the project, which was very interesting to provide a very long-term view of the actual impact of an operational impact on the appliance. So combining more than 3,000 hours of testing for the boilers and 2,500 hours for the cookers. This was done with 30% of hydrogen by volume in test gas. Of course, due to the long duration of test, there was less opportunity to have different test mixtures tested. So this was done on the equipment of 5 boilers and 2 cookers. And finally, there was a small part of the project that also looked at leakage tests. So from specifically the part of the network, which is at the very end before the customer, so the domestic and commercial gas line that goes to the appliance. Which was also 2 durations, one short duration and also longer periods of time. So the different parameters of the test program were to look at combustion, efficiency, safety, and the operational aspects, so also from the point of view of the user, was there anything significantly different in using their appliance with natural gas or with natural gas and hydrogen. The parameters that were varied were the percentage of hydrogen, the rate of change of the hydrogen percentage in the mixture, the natural gas composition, the pressure, and if the appliance had been adjusted or not. So we had several, for all of these different parameters to be tested during the test program, so which is quite a lot, with many different appliances, many different segments, so it was a major undertaking. There were some of the parameters that were more tested with more data than others. So we've had which was determined through the study of the actual appliances on the field. So the project focused on the most well represented, the most important gas appliances actually installed in the homes or in the businesses. So for the boilers, fully premixed, and the domestic cookers was the more well tested appliances. So we have a detailed result which is available from the project deliverables, and the data that was gathered on all the other equipment was also published, of course, but it isn't as exhaustive. So for the first type of test, the long-term test, the idea was to observe possible appliance alterations in the long term with the use of blends, which were monitored by measurement in the flue gas composition. The appliances were dismantled at the beginning and at the end of the test. with some visual observations as well. And the philosophy of the test was to simulate a real-life situation. So also with the duration of the test, but also putting the equipment through various modes of operation. So high temperature, possibly overload, etc. And this is, we have some pictures here of the actual test setup. So a cooker, the experimental setup for the cookers, and a heating, a boiler experimental setup. And here is some before and after, like in the ads, of those of the pieces of equipment, which were also allowed the visual observation of the impact on the pieces of equipment. The conclusions of this long-term test were that so the pieces of equipment tested were 2 cookers and 3 boilers, and by one company, and 2 boilers by another one. So all the emissions and efficiency levels stayed stable, which was a very interesting result. So there wasn't any quantifiable increase or issues related to the share of hydrogen, which was 30% for this test. There are signs of wear and tear, but that are consistent with the use with just natural gas. And we can conclude from this test that 30% hydrogen share didn't have any impact on the operation of the appliances. For the gas line tightness, so they want to test the possibility of leakage. Would it be increased with the presence of hydrogen, because hydrogen is of course a smaller molecule than CH4. However, for the parameters of our test, which were tested under 35 millibar, and the results were that 40% hydrogen and 60% of methane was the blend that was tested. And those under those specific parameters. So there was a short-term test and a long-term test, one for 10 minutes and the other up to 10 days. So you can see here the experimental setup. And the results were that at those relatively low pressures, which correspond to the reality of an installation in a home, there were no differences observed between leakage rates with air, helium, and the hydrogen natural gas mix. And we have some results from another European project, HyDelta, that have concluded that if no leaks are observed with natural gas and air, there shouldn't be leaks for hydrogen. And more than 200 hours of testing were done, and without an observation of deterioration of the components or loss of tightness. And therefore, we can also conclude this is very positive results that are consistent with normal operation of the equipment. In general, the THyGA project showed that for 20% hydrogen, taking aside the liability issue, which I will mention later, we have identified no safety risk for any type of appliance except for delayed ignition with some specific design of appliances, partially premix appliances without the fan. And adjustment of appliances is the main limitation. It only concerns fully premix appliances without a mitigation methodology, and we have in our deliverables detailed description of a recommended mitigation measure which could be applied to deal with this particular issue. So the conclusions are that for this project, which was interesting, that have a big collaboration between several European partners and a very extensive test campaign. Around 100 different appliances, a variety of systems, a variety of hydrogen and natural gas blends. But of course, that was just a small part of the whole range of installed appliances, and we could go, there could be funding programs that go further into exploring other types of appliances, other operating procedures, other types of gas blends. We have concluded that the blending up to 20% of hydrogen is technically feasible, but implementation would need a collaboration with the transportation companies, the energy providers, the member states. And finally, 2 topics should be addressed by all stakeholders: the liability and the adjustment. So first of all, the liability. So here we go a little bit out of the technical field, but into the real life field. So even though the technical results seem to point that installed appliances can technically cope with 20% of hydrogen, some reliability issues remain. So currently there are regulations that are in place, the gas appliance regulation, for example, and under it the existing gas appliances did not have to be designed for use with hydrogen blends. It wasn't foreseen. So hydrogen and natural gas blend supply cannot be considered as normal use. So manufacturers of those appliances would not be liable for any negative impact caused by the introduction of hydrogen to the system. Except some new appliances on the market which are today developed that are certified for 20% hydrogen or even 20% to 100% hydrogen, which is done by some manufacturers today in preparation for the switch of the networks. But the situation remains that for the appliances installed today, we have this liability issue. And the member states are working on methodologies and consultations to evaluate the percentage of hydrogen that can be injected with a distributed natural gas. And we need a harmonized decision of these methodologies and sharing of results to actually implement the blending in the networks. So this is the first recommendation of the project. And the second recommendation is on adjustment. So adjustment is an important parameter for blending. Apologies. THyGA showed promising solutions that are detailed in our deliverables. So some adjustments with oxygen, the instruction for the installers not to adjust the equipment when it is installed. But it is important to pay attention to national local regulation which could make more difficult this implementation. So this is an open issue that the project has highlighted, and it also needs to be decided in consultation by a range of stakeholders. At European level, we are actually at the moment having some discussion at the Commission and Parliament level on the hydrogen strategy, which will define the levels of blending or not that are acceptable, and then it will be a decision of member states. And then we need to have the collaboration between all the actors of the sector, so the transport companies, the manufacturers, and of course with the approval of the consumer population, which might be impacted by all these decisions. So that was for the THyGA project. We have, as I said, not only hydrogen as activity for our group, but it is part of the process that GERG is working on, is to identify common topics of interest, define those research topics, and we produce internally research roadmaps that are aimed at solving these common problems for the industry and the energy sector in general, and create collaboratively funded projects. Some of our publications are available on the website. An overview of GERG hydrogen activities, just to mention that we have here the THyGA project at the top. This is part of a portfolio of projects that has been developed over many years. So the part on utilization is very important. We are also working on the impact of blending on transport, on the materials, on mitigation of leakage, as methane, as hydrogen. We have the optics project, which deals with the detection of hydrogen leakage from a transport infrastructure using fiber optic technology, and a variety of different topics that go from the question of fundamental research, and our objective is to bring it to usable recommendations, in particular for the standards, which of course is the very important step to actually bring it to market and to reality. Just a mention of our portfolio of projects, which is quite large. This is currently our European funded projects, and some more are to come next year. So, as I've already mentioned, concerning hydrogen and biomethane and meteorology topics on CCUS, even hydrogen for transport. And to learn more, you can visit the THyGA website, which I would recommend if you're interested in the project, because everything has been published and all the data is open. The project partners did a very good job of also making the data sets available. So if you want to go and look into the actual results of the testing. We have also the GERG resources, so our social media, our website, and here's my email address if you have any questions. And finally, I wanted to mention this week we have the European Hydrogen Week going on in Brussels, so you may be aware. But if you're not, I would definitely recommend checking it out if you're interested in hydrogen. They still have, it's at Brussels Expo, and they have a lot of talks, a lot of events. The Energy Fair is still open until tomorrow, 9 to 8 p.m. And on Friday it's virtual. But it is very a very interesting visual representation of the impact of hydrogen in our energy system, because it is quite impressive the number of presenters and projects and talks that it is generating. And I will stop there. I'll be happy to take any questions. Thank you very much.
I might need some in a minute as well. I think the interesting talk and relatively short, which is not always the case. Sometimes I have to start tapping on my watch, and I think it's like the laird of the manor who, first of all, the minister gets very worried as his sermon is going on, and he shakes his hand to see if the watch is. But when he takes it off and actually shakes it to see if it's still working, then we know it's time to stop. But you didn't need that warning. Right, questions, please. Questions.
So you were essentially saying that in terms of domestic use and I guess commercial use, to 20% is good. Well, is fine. Yeah.
So that was a technical result. That's 20% from.
Is optimal, or is the one that is most easily attainable?
It is attainable. Optimal is a difficult question, because what parameters are we using? The idea was, I think, of the test program that maybe what would be optimal is the maximum percentage of hydrogen that we can introduce without anything going wrong, basically, because we would we like introducing more hydrogen because it makes if we assume the hydrogen is produced in a sustainable way, that means we are reducing our overall emissions. So if we consume more hydrogen, then it is better for the system. It's not technically optimal, of course. If you have at the moment the system works, so that's the optimal solution. If we introduce hydrogen, there might be some modifications to make, but indeed up to 20%, most appliances that were tested were functioning properly. This might not, and then after that there is more considerations that come into play, the liability question, which is quite difficult to resolve because everything that is installed, even though new boilers, etc., are now produced being hydrogen ready, but of course you have all the installed appliances that would need to be certified and converted maybe in a safe way. And the introduction of hydrogen into the network, so it is an ongoing debate at the moment. So some countries are very reluctant.
Skeptical is the word.
Yes, so it is really what we see now with our European partners, that there are very different positions. So in the Netherlands, for example, they're really thinking about not blending at all, but instead constructing or repurposing as part of the infrastructure directly to 100% hydrogen, without this step of having some hydrogen blended. and in other countries it is quite seen as a good first step. And the argument for would be that it is, compared to constructing a full hydrogen network, it requires a lot less. Even if you have to make some adaptations, can be done much more quickly.
Yeah. So I would imagine if the 100% hydrogen network, you'd need to have some very extensive testing if you use the current transmission system. Yeah. Because
Yeah, exactly. So we have, there are some parts of the system that can definitely be repurposed, so you don't need to build everything from scratch. But there are still a lot of the equipment, maybe not like the pipelines themselves, but a lot of the equipment at all the ends that need to be changed. There is a group of transportation system operators that are curating this program. It's called the European Hydrogen Backbone, and basically they have this I don't have them in the slides, but if you want to have a look, it's quite interesting to see. They have all these maps of Europe and which that will be the future hydrogen network that they are planning, which would be, and part of the pipelines would be repurposed, part would be newly constructed.
This was not part of your talk, but can I ask questions about how we are going to actually manufacture clean or green hydrogen?
Well, this is a bit outside of our scope of work. So,
but I just wanted to have your idea.
I'm no expert, but the idea, of course, why are we talking about hydrogen? Is because it reduces emissions at consumption, because the combustion doesn't produce CO2 as does methane, but it needs to be from a life cycle point of view. We need to reduce emissions overall. So at the moment we have hydrogen produced from natural gas, which doesn't solve our problems. So of course would be through electrolysis, linked to, for that you need electricity, and the idea is to use electricity that is produced from renewable means, so solar, wind, and of course, and there is a little bit of you might think that if we have renewable electricity, why not just electrify everything and use the electricity directly? And that is definitely something that can be discussed. But one of the advantages of hydrogen is that it's a gas, and so it can do things that electricity can't. In particular for the intensive industry, highly energy intensive industry. So you can't electrify a steel plant, for example, but you could have. But you could use hydrogen in priority in certain applications, and also there is the question of renewables being intermittent. So you have periods where you have a high production and then a low production, and sometimes you have an excess. And if you could, hydrogen would be a great way to convert this excess electricity and to store it in a way that
instead of trying to store it in batteries.
Instead of batteries, and have the transportation of hydrogen, have pipelines of hydrogen instead of, for example, from offshore wind farms. That is one of the applications, that you have this production of electricity offshore, and you can transport it to shore through electricity cables that are quite difficult to make and have to go offshore.
Creating a lot of problems on the east coast of England. Yes. We've been in Norfolk and Suffolk recently. That's a big...
And replacing that by a conversion to hydrogen on site offshore, and having a transport by a hydrogen pipeline is more economically interesting.
Can I come back to your lecture? If I read your slides correctly, long term is 10 days. What about 10 years, or even 100 years?
Well, we at the scale of the project.
We won't be here, but I mean, you can do accelerated testing. And I'm interested to know what materials are at risk for such factors as hydrogen embrittlement. I know it's a function of temperature and pressure, but in existing equipment, what are the materials at risk?
Well, I don't have that in the slides. There was testing done on embrittlement. I think indeed at the scale that the tests were done in the project, they didn't highlight any material failures of the equipment. In general, if we talk about pipelines, for example, for which there are studies, steel pipelines are definitely at risk of embrittlement, and so this is not, steel pipelines are not considered for hydrogen at all, also because of leakage. And then after that, metallic components, so the best case for hydrogen is polyethylene materials. And in terms of the lifetime of this test and the impact over a very long period of time, in this case we're talking about boilers and cookers, so they do have a lifetime of their own, which wouldn't be 100 years, could be couple of decades still. So, but yeah, so the product tries to simulate a representative length of time. Of course, you can always go further.
Because I'm just replacing a boiler which is 44 years old, functioning pretty well, by the way. I just decided it was old enough.
Yes, Harry.
I'm an organic chemist, so I'm speaking for my organic friends. In other words, the natural gas molecules, what happens to them when you burn them. I'll frame my question a bit. About 40 years ago, I was involved in the development of oxygenates for replacing the anti-knock compounds, metal compounds in gasoline. And therefore we were studying things like what happens to whatever you burn inside an auto engine, where the burning temperatures something about 900 degrees or so. And we observed that when you moved to oxygenates in the gasoline, you still get some coking deposit formation in the engines over long term. Now my question is that when you were adding hydrogen to the natural gas, the flame temperature went up in the cooker hub, and slightly up also in the burners. Did you study what happens to the coking, the deposit formation over long term? Because this might be something that actually lengthens the lifetime of the devices.
Yeah, thank you for the question. I would have to check. I don't think that specific question was part of the different parameters that were studied, but I can check, and I can have a chat with the colleagues in charge of the testing.
I'll send you an email.
Yeah, please.
Yeah, good idea.
What will be the price of this new gas? Cheaper or more expensive than the corresponding?
Well, it depends. I can't give you any numbers because it's out of the scope of the project, definitely, and what we are looking at the moment. There is it depends on the supply, really, on the supply and on the technology. I know a lot of effort is being made at the moment to ramp up the hydrogen supply for Europe by domestic production, electrolysis, and also imports from neighboring countries that have opportunities to produce it also in a clean way. For example, from the south of the Mediterranean, there are some plans actually to have some use of the solar energy, which is quite easily accessible over there, to have some production of hydrogen and then transport it to Europe. So we'll see. But of course, that is a very it's important question for the impact on the consumer. That is always the big question for the energy transition in general, of course.
With the development of technology, new equals more expensive.
Inevitably. Yes. Other questions? Massive silence. Yes.
What's the specific project you're going to be working on next? Do you know what the specific project you're going to be working on next is?
Yeah, so we have a lot of projects ongoing. Some interesting examples. We have the optics project that I mentioned. We have which is also European funded. It's called the Clean Hydrogen Partnership, and it is dedicated to detecting hydrogen leakage from pipelines, which was of course commissioned by the European Commission and the funding program, because it is something that needs to be really checked before we put hydrogen networks into operation. And hydrogen is a smaller molecule than natural gas, so we have to see if our existing systems are adequate for detecting leakages and for preventing them. And that specific project is looking at a very innovative way, which is to use fiber optic technology. So you're running, which is interesting because it is not you are running this fiber optic line next to your pipeline, basically, and thanks to a specific coating on the fiber optic strand, you can that will react to hydrogen if it gets emitted. You can then analyze the signal that you get back, and so make the detection quite efficiently, and also without any moving parts or without any equipment on the pipeline, and you can cover quite a long distance of the equipment with the system. So we're quite excited about that.
Just wanted to ask, in your opinion, how long it would be how soon we might be able to convert to the technology, say in Belgium?
Yeah.
Are we looking 10 years, 20, 5?
Yeah, no, thank you for the question. I think that it might actually, well, we'll see, it depends also on political decisions and economic decisions, but always. But it might actually go quite fast, because we have the technology is not that far away. There are some things that need to be carefully checked because we're dealing with safety, so of course you want to make sure everything is well managed and certified, etc. But the technology is not very far for hydrogen blending. On hydrogen boilers, for example, are on the market today. So this is very much feasible. Then economically feasible is another question. And there is also a political impulse, I think. Yeah. I mentioned the hydrogen conference week. If you visit, you will see also a lot of presence from politicians, European level, national level. So it might be quite soon. I think in 10 years, I think we would see something very concrete.
There have been some of the energy suppliers in Belgium who have been contacting customers, telling them that they're going to change the gas quality.
Well, it's interesting because
I think we're talking about hydrogen, but
the
we're
gas
talking
meters are all on Ivory House they're working through changing them for new ones. I wondered whether this could also.
I think it's related.
Related.
I'm not sure it's going to be directly hydrogen, but there's going to be a change in the composition of the natural gas that we're going to be using. I think that's coming along.
And speaking of detection, we live fairly near a high pressure natural gas line. And once a week a helicopter comes over low to check for leakages. So
every day at 1 o'clock.
Every
day at 1 o'clock.
No, we only get it once a week. So
It was a leaky one.
You have a daily check?
Yeah, I can set my watch by it.
That's very interesting. Yeah, we've actually worked on a project for methane, in this case just standard natural gas emissions verification, which is also, there's been last week or 2 weeks ago, a new strategy came out by the European by European regulation, which is going to be about new rules for methane emissions detection and reporting. we participated in a project that was looking at different ways to do that. So there's a helicopter, which is very nice but costly. Of course, you have to have an helicopter to the rounds, and you can have systems embarked on cars and stationary systems. So
Interesting. Yes, John.
Quick question. You say the Netherlands think about moving to, if they move to 100% hydrogen, if they had domestic cookers with 100% hydrogen, would they add something to it so that a domestic customer could detect if it was leaking, if they had a leak? Because obviously with methane they add something to it, so you can smell if you've got methane. With the hydrogen, what are they going to add to it?
Yeah, definitely. I mean, this is under development, but there are studies on odorization for hydrogen. And I know some companies that are our members are working on how to make sure that this mixture with the odorant molecules is behaves in a way that is consistent. But of course, when you do, because the customer being able, the citizen being able to smell the gas is basically the first method of detection from the gas companies. So
that's why they used to put sulfur compounds in it, isn't it? So you could detect it when it was leaking. Right, if that's your lot, then thank you very much indeed for your talk, and just a little gift to thank you, which will give you something to enjoy after the talk. And thank you once again. Our next events will be the annual general meeting of the section, which will be in January, and then the Café Chimique, which will be on artificial intelligence, where we will endeavour to have two speakers, one of whom will be fanatically convinced that this is the best thing since sliced bread or canned beer, whichever you prefer, and the other who will no doubt tell us that it's the devil's own work and it will end up taking us over and driving us mad. So we will see what comes of that. But you keep an eye on the blog and you'll see them coming up.
Okay.
And now I invite you to join the speaker and have a chance to chat informally over a glass of something or other. And thank you all again, once again, for coming, and look forward to seeing you soon.
Thank you very much.
Thank you.